I would like to take a few minutes to talk about the radical addition of Hbr. And we've seen this before back in the chapter on additions to alkenes, right? If we take an alkene, we take Hbr, we add it, mix them together, we expect to get Markovnikov addition of that bromine, right? And that's no radicals, no peroxides. And if you remember, we learned that if you add peroxides to this reaction, you can get the opposite regiochemistry, where we get bromine added to the less substituted side of the alkene. We get Anti-Markovnikov addition, and this is with peroxides. And typically we write ROOR here to designate peroxides, but it could be H2O2, it could be tertiary butyl peroxide, where each of those R's is a T-butyl group, or it could be a number of other peroxides. So what I want to do now is look a little bit more at the mechanism of this using some of the radical arrow pushing that we've worked on over the past few videos. So as we learned, the first step here, we need to make some radicals. We need an initiation step. And that's going to be where we take our peroxide, whatever it may be, and we split it in half. And we make two RO radicals. And this is homolytic cleavage. If you're following along with the 6 different types of radical patterns. And now that we've formed some radicals, we can now do some propagation steps. So our book calls this next step initiation as well. I consider it more of a propagation because we're taking a radical and we're creating more radicals. So if we have the RO dot, we can react that with Hbr. And we can create ROH and a bromine radical. And this is hydrogen abstraction. And now I have ROH, which plays no more role in the reaction. And I have the bromine radical, which is now my active radical species. And so I'm going to try to use some different colors here. This is initiation. I'm going to call this propagation. Like I said, our book does consider it to be initiation, but I'm going to argue that we started with a radical, we ended with a different radical. That fits my definition of propagation. So let's look at what we can do with the bromine radical now. That can react with our alkene in an addition reaction, and we're going to form the most stable radical at the end of the day. So this is going to be addition, and we're going to react like this. Basically, we're going to form the radical at the more stable tertiary side. And now, again, I would consider this propagation because we are taking a radical, reacting it with a non-radical, and producing a new radical. And now I can take this new radical and redraw it here. And I can react that with, I can react that with Hbr in another hydrogen abstraction. To produce my final product. So this radical is going to form a new CH bond with the hydrogen portion of Hbr, and the bromine will form another bromine radical. And again, this is also propagation because we've taken a radical species, reacted it with something that's not a radical to produce a non-radical and a new, different radical. And I want to point out this bromine can be used in another step here to produce another radical intermediate. So now these two steps can repeat as long as we have enough Hbr around. This is our product. I'd like to point out this new stereocenter here is going to be both versions of the R and the S. So let me put a wedge here, and then let me put a plus minus to indicate we get both versions. We're going to make a racemic mixture of this product because during a radical reaction we have no control over stereochemistry. So if we create a new stereocenter, we will create both R and S versions of that in equal amounts. So this is the end product. But there are some final steps that we could consider, and that might be termination steps. Maybe the bromine, just by coincidence, comes into contact with another radical like this, and this is unlikely because the concentration of radicals will be very low. And of course, this is a undesired reaction. It doesn't produce our product, but this would produce in very low percentage. Another termination step might be the bromine. So we have to look at what other radical species we have. We have the bromine, we've got this radical intermediate here, the same thing. Here's the bromine there. We have an RO dot, but the reality is there's not a lot of peroxides that we add to this reaction mixture. For instance, if we started with 1 mole of alkene and 1 mole of HBr, we might put 0.01 moles of peroxide. We really don't need much. We only need enough to start this radical chain mechanism so we can have a small concentration of radicals at any one point that can continue to react with non-radical species propagating that radical. So this is very unlikely to happen here, and it's also unlikely that the bromine would encounter another bromine radical and they could react to make bromine molecular bromine. This is also termination. And if you're asked to draw the radical mechanism for this reaction, I would expect you to draw, sorry, let me underline these because that should be in red. Those are termination. These are also called coupling reactions if we're following along with the radical mechanistic steps. So I'm going to call those coupling, compare that to hydrogen abstraction, addition, homolytic cleavage. So the first 4 steps that are shown here are the important ones in this reaction mechanism because they show us how to get to this product. So if you're asked to draw the mechanism, the first 4 are what I would expect to see. The last 2 here, termination, we just draw to show you how we might run out of radicals. How that might occur, again, because the concentration of any one radical is very low. These are unlikely to happen because the one radical would have to encounter another radical within our reaction mixture, and because the concentration is low, that's very unlikely. So here is the overall mechanism for the radical addition of HBr to an alkene, and it helps support the anti-Markovnikov outcome that we know about because scientists have run this reaction in the lab and analyzed the outcome, and that was before they knew the mechanism. So generally, as we've learned in class, scientists will, if they encounter a new product or an unexpected product, they study it, figure out what the structure is, then they propose a mechanism so that we can predict that outcome in the future with different shaped products. Like now we could use any alkene here, as long as we have HBr and some peroxides, we know that we can get anti-Markovnikov addition of the bromine, and that can be a very powerful tool to have in our toolbox.